levels. One is the bottom of the conduction band across the device, which is ECP and ECN in the PN junction. ECP is the conduction band on P side, ECN is the conduction band on N side. And similarly, the top of the valence band is EVP and EVN. And there is one more level, which is known as the Fermi level. And this Fermi level tells us about the energy of electrons in this device. So if the Fermi level is flat, Fermi level is uniform across the device, it means that the electrons across the entire device have the same energy, or the net energy of the electrons is the same. Or in other words, in terms of statistics, it means that the distribution of electrons, the statistical distribution of electrons across the entire device is the same. And if there is a disturbance in the Fermi level, it means that this equilibrium distribution is disturbed. Yeah, so do you have any question up to this point?
So,
Yeah, if not, please switch off your mics so that there is no unnecessary noise. And this is the current expression for the diode. We did not derive the expression because that is sort of we cannot go into that kind of details here. We need to cover a lot of different topics, and but this expression captures various dynamics. It captures the hole diffusion, it captures electron diffusion, electron drift, Hall drift, all these kind of things. And this IS is an interesting parameter. IS is the reverse saturation current, and it is present both in forward bias and in reverse bias. Okay, and generally it is also independent of the applied voltage, because last time we saw that this IS is very quickly it achieves its saturation level. It achieves this flat level. Okay. In the previous class, we also saw that there could be two types of breakdown in the diodes. One is because of the tunneling of electrons from N side to the P side, and second is because of the high energy of the carriers in the system. Okay, and these are known as the Zener breakdown or avalanche breakdown. So this is mostly about the IV characteristics of the diode, and for a silicon diode, the voltage at which this current in forward bias becomes extremely high, this voltage is around 0.7 volts. And that is also known as the cut-in voltage of the diode. So that is the voltage after which a very high current starts flowing in the circuit, which means that the diode behaves like a short circuit after this voltage. It behaves just like a wire. And before this voltage, there is not so significant current in the diode, and especially for the lower voltages, the diode is almost off. And even for negative voltages, the diode is almost off, because this IS current is very small current. It is just few microamperes. And this forward current is in milliamperes. It's a large current. So that's why this diode has the rectifying characteristics in a way. Rectifying means that it conducts current only in one direction. In other words, it allows current flow only when a positive voltage is applied across the diode. When the negative voltage is applied across the diode, the current flow is extremely small, almost negligible. And if we connect this to our previous discussion, we saw that in the beginning, by the end of 19th century and the beginning of 20th century, the AC current production was very much popular. It could be easily transmitted to long distances, and at that time, both AC and DC production and supply facility was there. But But so this kind of device, the device which can convert AC signal to DC signal, was extremely sought after. Extremely, it was urgently needed because that way we just had to produce AC current, and finally we could convert AC to DC so that the electrical appliances working on DC current can also be used. And initially, a vacuum tube diode was used as a rectifier, but finally, after the invention of the PN junction, this quickly replaced the electrical rectifier. Okay, and moreover, this was also important in RF in communication that you possibly will see when this the communication part of this course is discussed. Okay, so this discussion was done keeping silicon in the center. We always had in the back of the mind that this is a silicon diode. This is P-type silicon on one side, N-type silicon on other side. But let's try to see how these characteristics would change if we have a different material. Let's say so. I told you that these three uh, semiconductor are popular semiconductors: silicon, germanium, and gallium arsenide. And the difference in these semiconductors is of band gap. Okay, so their band gaps are different, and as a result of that, the intrinsic carrier concentration, which means that the free electrons and holes are also different. So, for example, this gallium arsenide band gap is more than the silicon band gap, and as a result, the intrinsic carrier concentration is less. In silicon, the intrinsic carrier concentration is around 1.5 into 10 to the power 10. If you don't recall, the intrinsic carrier concentration is the number of electrons, number of free electrons in a semiconductor without doping at room temperature. So these are in a way thermally generated electrons and holes. Okay. So let me sort of allow you to think what would be the current, for example, how would the IV characteristics of a gallium arsenide diode look like, and how would it be different from the silicon characteristics? Can any one of you uh, guess what will be the difference in IV characteristics of silicon and gallium arsenide?
The reverse saturation current will decrease in gallium arsenide.
Yeah, that's one point. It will decrease, and the reason for that is, Dikshant,
Sir,
what
because
is the reason?
minority carriers will decrease. Minority carrier will due to intrinsic carriers like.
Okay, okay, yeah, yeah, that's an interesting point. Yes. Anything else? Anybody else wants to add?
Sir, forward current should also be less initially because of less number of uh, majority carriers.
Forward current will also be less in the case of.
Sir, in gallium arsenide, because there are less electrons initially, so
Mhm.
initially it should be less, but after breakdown, there will be not much difference in that.
Okay, okay, yeah, that's also quite important. That's very good. Yeah. Yes. So similarly, we can think about uh, the germanium as well. And so these are the characteristics of IV characteristics of silicon, germanium, and gallium arsenide. And as pointed out by a couple of you, that the reverse saturation current will be less in gallium arsenide, which is also evident from this plot here. At the same time, the forward current is also less for the same applied voltage. Actually, if we apply the same voltage on silicon and on gallium arsenide, uh, the current is less in the case of gallium arsenide because the number of charge carriers is less. On the opposite, the current is more in germanium because there are a lot of charge carriers and uh, current can easily or current quickly increases. So this is the comparison, or this is the band diagram or band gaps of silicon, germanium, and gallium arsenide. So as the band diagram or as the band gap increases, the IV characteristics also shifts towards the right in forward bias and upwards in reverse bias. Okay, is this clear? Is this part clear? If not, please ask questions.
Sir, why the value of VD is greater in case of gallium arsenide than in case of silicon? As
Value of
the intrinsic carriers are greater for silicon, so sir, for VD must be greater at when the breakdown is happening.
VD, by VD you mean this cut-in voltage, the voltage
Yes,
at which this happens. Okay.
yes,
Yeah. So are you asking for a mathematical explanation or intuitive explanation?
sir. Intuitive. Sir, I think as N is increasing, N is greater for silicon, so VD must be
Hmm.
greater, so that they will uh, means the breakdown will happen at sir peak voltage as for sir
Breakdown will. No, you are.
germanium
Which
sir,
breakdown are you talking? You are talking
the
about
right side.
the.
No sir, no right.
Yeah, yeah. So this is not a not so. This is not called breakdown actually. This on the right side. Generally, this high voltage when it is applied on the high negative voltage is applied uh, on the diode, it is known as the breakdown of the diode. Okay, in the reverse.
Okay sir.
In forward bias, it is known as the on state. So you are saying that why is this on voltage more than for gallium arsenide as compared to the or the
Yes,
cut-in voltage for
yes,
this? Okay. So that actually, yeah, that's also an interesting thing to think about, and that depends on the depletion region and ultimately this barrier that is created in the diode. So for the same doping, so let's say if we dope silicon and gallium arsenide with the same amount of doping, this barrier height would be more in the case of gallium arsenide, and the reason for that is uh, this band gap. So, for example, if this band gap is more, then this height also changes more because this needs to come down more in order to align with the left side. So we need ultimately we need to align the Fermi levels on both sides. And if the band gap is more, in that case, it needs to come or it needs to make a bigger hill, bigger slope, and that's why. And as a result of that, this depletion region is also different, and that's why this V naught, the barrier height is different, and more in the case of more band gap, and that's why this cut-in voltage, the voltage at which the current becomes sufficient, is actually high in the case of gallium arsenide. That can be understood from the band gap of these materials.
okay.
Okay.
Sir, in the IV characteristics of the negative side, is the breakdown we are seeing here, is it Zener breakdown or is it avalanche breakdown?
It is avalanche breakdown actually.
Okay, sir.
For Zenith breakdown, generally we need to have a specific dimensions, specific geometry of the device. And just to sort of point it out here, that the voltage that is written on this axis, it is around 50 volts, 100 volts. Okay, do you see this? So that is
Yes.
typically the order of the avalanche breakdown voltage. The
Okay.
Zener breakdown most likely takes place around 3, 4, 5, around that value.
Okay, sir. Got
Okay. So I think this thing is done. This diode physics, diode IV characteristics is done. Let's have a quick look at some of diode applications actually. So till now we have been discussing the abstract PN junction. We did not discuss very concrete applications of that device. Although I pointed out that it is a very good rectifier, but there are some other interesting applications as well. Can you uh, point out some applications? Do you,
Sir,
apart
LEDs,
from,
Sir,
cell.
LED, solar cell,
voltage
photodetector.
regulator.
okay, yeah, those are among the most common or most widely used, uh, I would say, avenues where this diode PN junction is used nowadays, because in most of our electronic appliances, we generally have transistors, but in solar cells and especially in LEDs, photodetectors, lasers, we have we still use PN junctions. We still use. So, are you aware how these devices work? Are you aware of their inner physics?
It's a very basic one.
Yeah, can you please
So like in
describe?
solar cell, we allow the light to fall on the depletion region, and that light creates new pair of holes and electron, and they are drifted by the already generated electric field, and so we are now able to generate current and voltage and thus current. And in LED, uh, when a new pair of electron and hole are created, and when they recombine, they create energy in the visible region, and so light is created. So just like that basic.
Okay. Anyone else wants to add anything to this? Yeah, that's a very I would say that's a very surface level explanation, but that's the right explanation, I would say. If somebody asks you, then this is the way you explain them in the beginning. But do you see or can you now see the role of diffusion and drift? So we have seen in a diode, in a PN junction, that how the carriers essentially moves around. So there is a diffusion of majority carriers and there is a drift of minority carriers. This diffusion happens because on one side we have a large concentration of certain carriers, and on another side we have very small concentration of that kind of carriers. The drift happens because there is an inbuilt electric field at the junction, and as soon as any carrier or any electron hole pair is generated or comes in that region, that is swifted away. And as you just pointed out, that there are two kind of devices. One is LED, second is solar cell. In one device, we need to, in solar cell, for example, we need to create electron hole pairs. We need to have current. The input is light and output is current. So we need to have generation of carriers. And in other device, LED, we need to recombine the electron hole pairs, or electrons and holes need to be recombined. Okay. So the point here is that one of that devices, especially the solar cell device, that essentially works on, or that has the drift of electrons and holes, the carrier drift at the center, of its mechanism. And the LED essentially uses the diffusion of carriers. So LED in a way is a majority carrier device, and solar cell uses minority carriers for its operation. So that's the essential difference between the two, and that is the reason that let's have a quick look at how they actually work. So, so this is a typical LED. We have a P-type material and type material, PN junction, and in this, if we apply a voltage across it, it should give us light. That is how the LED is defined. On application of electrical signal, it should give us optical signal. So, so should we apply a forward bias or a reverse bias? What do you think in this case in LED?
Forward bias.
Yes. Anybody else?
So forward bias only.
What is why do you think so?
So because we need drift current.
In LED?
Sorry, sir, diffusion current, sorry.
No, but why do we need diffusion current in LED?
Sir, because when electric field will push the carriers towards the junction, then new electron hole pairs will be formed, so they can recombine there.
Exactly. So that is the point. Yeah, you're right that we need diffusion component of the current, because that component essentially pumps more number of electrons and holes in the junction, because as soon as we apply a positive voltage, it reduces this barrier, and now electrons from N side can go to the P side and holes from P side can go to the N side. And once this uh, transport of carriers from one side to other side starts, then they can potentially collide and recombine with each other. However, in negative, if we apply negative voltage, it does not increase any flow of carriers actually. The carrier flow does not increase it. Moreover, it reduces the carrier flow. Okay, so that's why we apply a positive voltage, so that a lot of carriers can now diffuse from one side to other side, and in the junction they can possibly recombine with each other, or maybe outside the junction also they can recombine, but most of the recombination takes place in the depletion region at the around the junction. And if you remember the notion of direct and indirect band gap semiconductors, if we use a direct band gap material, then on recombination a photon will be emitted and that will produce light, right? But if we use an indirect band gap semiconductor like silicon or germanium, then on recombination, most of the energy might be produced or might be transferred to the phonons, to the lattice vibrations. So this point I also highlighted at that time, that in making LEDs, we typically use direct band gap materials. So that's why this gallium arsenide or gallium nitride, these kind of materials are used. All right. So in LED, in summary, what we can say is, as soon as we apply a positive voltage, it reduces the barrier in the LED, and that results in a lot of carrier diffusion across the junction, and that also results in recombination of electrons and holes, and that gives us light. Okay, that is the very basic function of the LED. Any question here?
Sir, but why we say that major recombination is occurring in the depletion region? Because shouldn't it be in P region, because there are many holes and electrons are coming from N side?
No, so even many holes are coming from the P side. So So this barrier, as soon as this barrier is reduced, as soon as this barrier goes down, there are many holes that starts from here and they try to go to this side. So as if there is a flood of electrons from one side, flood of holes from the other side, and the first thing, or most likely encounter happens in the depletion region around the junction. Although what I'm saying is that is not the full picture. Some of the electrons can penetrate deep to the uh, into the p side, and there also they can recombine actually. But most of the recombination, because uh, most likely they will get in proximity with each other in the depletion region itself. So that's why this contribution is more in the depletion region.
Okay, sir.
So why don't
Yeah.
we take the recombination of electron and holes in all the cases in forward bias?
Uh, yes, yeah, that's a good question. In all the cases, you mean why don't we take it into account in silicon diode as well?
Yes, sir.
Is that right?
Or
Yeah. So yeah, even in any diode, that actually happens, and that is also the reason. So for example, when we apply a positive voltage, you might have seen that diodes heat up actually. So generally we use silicon diodes, and since silicon is an indirect bandgap material, so this recombination energy is converted in the lattice vibration energy, and that's why the diode heats up. So
so
that
when
is
we
always there.
use
This recombination is always there.
so when we use a diode as a rectifier, then also this recombination is there. Then why don't we take it into account
So it is
as a
taken
major
into account.
phenomena?
Yes, yeah, you're right. It is taken into account. It is always, while we do the detailed physics of the diode, this is always taken into account. And generally, and this is a good question, I would say, because uh, then a simple diode, the design of a simple diode and an LED diode is different actually. The doping amount is different because in LEDs, typically we need to have high recombination, so we need to have high doping, and even we can have graded doping actually if we need to have recombination in a certain. But let's not go into the graded junctions at the moment. In simple diodes, the doping is done in such a way that that it achieves. For example, if we want to use a diode for rectification, so we will do doping not so high so that the recombination is very high, but not so less so that this diode function is also not there. Okay, so there is slight difference in that, although the recombination is always there in all kind of diodes. In some diodes, it may be less. In some diodes, it may be more. And in LEDs, by design, we want it to be more. And in silicon diodes, where we do not have any light emitting from the diode, we want it to be less. We want the recombination to be less. So that's why the doping is done in that way. Okay. But you are right, it needs to be always taken into account, and it is taken into account.
So what are the factors that affect the intensity and wavelength of light emitted?
Yeah, so yeah, that's also a good question. And yeah, maybe I'll ask you back, not to you, but to your friends. What is the intensity of a light signal? How do you define intensity?
So in terms of energy, as amount of energy falling per second per area.
Yes. So yeah, anybody else has anything to add to that?
Sir, I think it's closely related to the number of photons emitted per unit time.
Exactly. Yeah. So the amount of energy is actually the depends on the number of photons. So if the number of photons are more, the intensity is more. Number of photons is less, it is less. But what is the wavelength dependent upon? So yeah, we know that intensity is directly proportional to the number of photons. But what is the wavelength depends on? What does wavelength depend on?
Energy of that photon.
Energy of a single photon, yes. And what does would energy of a single photon depend on?
The energy emitted when it recombines at electron hole.
And what
Energy
is
difference.
the yes? What is the energy difference between the energy of an electron and hole?
Sir, the band
So
gap.
the band gap.
Exactly. So, to answer your question, the wavelength of the emitted light depends on the band gap of the material. Okay. If the band gap is more, energy is more, wavelength is less, frequency is more. If band gap is less, wavelength is more. So the color of the LED or the color of the emitted light depends, the color depends on the wavelength, and that depends on the band gap of the semiconducting material. And in that also, I would just, since this question has come up, I would just like to add here that nowadays we see LED of different colors. And the reason that we are able to make LEDs of different colors is that we are able to make semiconducting materials, direct bandgap semiconducting materials of different bandgaps. And that is done. So this gallium arsenide material can be, we can have indium gallium arsenide, we can have this composite kind of semiconducting material. And by changing the amount of indium and gallium in the material, and okay, and by changing the concentration, the molar concentration of these three materials, we can tweak the band gap of the semiconductor, and then we can change the color according to that. Okay, is it clear, or
Excuse me, sir.
do I need to? Yeah.
Sir, is there any relation between band gap voltage and the cutting voltage?
Band gap voltage. What do you mean by band gap voltage?
So like I am expressing the energy in terms of voltage, the difference in energy.
So you are saying that what is there a relationship between band gap and cut-in voltage?
Yes, sir.
Yeah. So as I said, this cut-in voltage, it depends on the band gap definitely, but it also depends on the doping. Okay. For the same doping, if we do the same doping in silicon, so in order to make a diode, we need to do doping. Okay. And for the same amount of doping, the cut-in voltage will be higher for higher band gap. And the reason for that, as I explained to you, is that this barrier height will be more for a larger band gap material. This barrier height will be more. But if the doping is different, then cut-in voltage may be different as well. So it may also happen that the cut-in voltage for high band gap material may be less because the doping might be less as well. Okay. Is it clear?
Yes.
Okay, so this LED thing is it clear, or do we need to? Do you have any more question in this? Any type of question, please ask. Any kind of question. So this gallium arsenide LED, just a matter of fact, they emit light in infrared zone. So it's almost invisible actually. But I guess, although I'm not sure, that this is, I guess, the same kind of LED that is used in the TV remotes. Although I need to check, you can also check it. Okay. And the gallium nitride LED that emits light in the blue region, actually the blue light. And just a matter of fact, again, this blue LED was actually extremely difficult to make till recent time, still last few years, because it was not easy to make a gallium nitride LED. Gallium nitride is a difficult material, I would say, and because of the absence of the blue LED, the all possible combinations of colors, RGB combinations, were not feasible actually. So the LED display was not so good until this blue LED was discovered. But as soon as this blue LED was commercialized, then these LED displays in our televisions, in our mobile phones, those actually got improved a lot, because now all possible color combinations could be uh, manifested by the LED combinations. Okay. The red LED and yellow LEDs were already there. They could easily be made, but this blue LED was the most difficult one. So we cannot sort of underestimate the importance of LEDs in our modern day appliances. It is used everywhere. All of us know that it is used in displays, mobile phones, TV, laptops, computers. It is used in lighting. So almost the entire world is now lit with LED lights, or large part of the world. So it's that important. It's also energy saving as compared to the previous thermal bulbs. So this has been an extremely important invention actually. The LED lighting and LED display has been an extremely important invention that came out of this the diodes, basically PN junction. Okay. Any question in this? Any clarification? Or anything that you want me to repeat? If not, now let me ask you, how should a solar cell function? So solar cell is a device that uh, on that solar light shines. We shine solar light on the device, and it should produce a current or voltage across the terminals. So if you are given a diode, how would you make a solar cell out of that?
So it can work exactly the opposite of LED, where you will connect it to two terminals and connect that to a battery. So whenever light falls on the solar cell, then an electron hole pair will be generated. When it recombines, then current will flow. Sorry, it
When
doesn't
it recombines, sir?
it will not recombine. That will the current itself will get stored in the battery, because that electron hole pair.
Yeah, but how is that electron hole pair converted into current?
Sir, because of the depletion layer, sir, the electron will go in one direction, the hole will go in another direction, so it will create a current, and that can be stored later by in a battery.
Yes, yeah. Okay, yeah, very good. Anybody else?
So we would also need to widen the depletion region so that maximum electron hole pair are produced.
Yeah, so yes, you have got it, and that is exactly how a solar cell functions. A light, any kind of light can shine on the device, and if the frequency of the light is sufficient to create an electron hole pair, the frequency of the light is more than the frequency corresponding to the band gap of the semiconductor, then it can create an electron hole pair. But now the job is that we do not want this electron hole pair to recombine back, and we want to quickly separate the electron hole pairs so that we can produce a voltage across the device. Okay, so this making of a solar cell is a game in which we want to quickly produce or quickly separate the generated electron hole pairs. And there is a basic principle of physics that actually stops, or that comes in this way, in the way of working of solar cell, and that is known as the stimulated emission. Have you heard about stimulated emission? You might have read that in lasers, the theory of lasers, that if a photon can create an electron hole pair, or photon can excite an atom, it can also de-excite the atom. Do you know this or not?
No, sir. So we haven't been taught lasers.
No, but in your JEE preparation or in your 12th classes, you might have seen this, heard this.
No, sir.
Not of this specific concept.
No, sir.
Okay, so this essentially comes from quantum mechanics, but this is a very popular concept. And the concept is that the atoms can be excited by the photons. So this concept is actually from the light atom interaction, light matter interaction, in which the photon and the interaction between the photon and electrons is studied. So generally, all of us know that when a photon of certain energy falls on a material, it can excite electrons in that material. Okay, we know this. But the quantum mechanical principle also dictates that if the atom is already excited, the same photon can de-excite it, and two photons will be generated. So for example, the electron is sitting in the higher energy level. The photon of certain energy comes up. It hits that electron. The electron can go down, and so there was one photon that was coming from outside, and one photon is created because the electron now goes down. So there are in total two photons that are emitted from the system. And this is known as the stimulated emission. And this is actually the fundamental principle of the laser. That's how the light is created in the laser. Because we have a lot of electrons, excited electrons in the laser, and then when one photon de-excites one of the electrons, it creates two photons, then two photons may de-excite two electrons, it creates four photons, and that way a lot of photons are created, and that's how a concentrated beam of light is created. Okay, but we are not concerned about the lasers here. The problem is that this basic property or basic nature of electron photon interaction, in which the photon can excite the atom and it can also de-excite the atom. That is actually one of the major roadblocks, major problems in solar cells. So in solar cells, what happens is that incoming photons, they create electron hole pairs. But at the same time, they can also recombine, they can also maybe recombine them. So there is a certain probability of that happening as well. So that's why the efficiency of solar cells cannot be 100%. That is prohibited by the physics, by the principles of physics. But apart from that, we can try to, as soon as an electron hole pair is created, we can try to separate it. Okay, and we can try to have a better solar cell. So the basic principle of a solar cell is that we have n-type material, p-type material, and the depletion region is there in this material. And so the way this structure is shown in this way is that one of these is small. So for example, the p region is small here, so that the lights can go up to the depletion region, and it can create electron hole pairs in the depletion region at the junction. And at the junction, if the electron hole pair is created, that will be drifted away. Actually, if the electron hole pair is created in the neutral region here, then it may again recombine back. It will not be separated. But if it is created either in the junction, either in the depletion region, or very close to the depletion region, then only it will be separated. And electrons will gather on one side, holes will gather on the other side, and that's how voltage is generated across the diode. Okay, so that's the essential mechanism of the solar cell. Now, if there is any question, please ask. Please let me know.
So can you please repeat the last part? I could not get it. Why the electron hole pair should be generated at the depletion region?
Okay, so let me go to this diagram here. The electric field in a junction exists, electric field in a PN junction exists only in the depletion region. Okay, so this is the depletion region, and these are the quasi-neutral region, or these are known as the neutral regions. Okay, there is no electric field in the neutral regions. So if the electron hole pair is generated in the neutral region, they will not feel any force. So they will not be separated from each other, and they can eventually recombine. Okay. But if the electron hole pair is generated in this depletion region, there is an electric field, and because of the electric field, both of them will feel a force in opposite direction. So electrons will go in one direction, holes will go in other direction. And that way they are quickly separated from each other, and this possibility of recombination is ruled out. So that's why we want the electron hole pair generation to happen in the depletion region in solar cells, so that the electrons and holes can be separated from each other. Is it clear now? Is it more or less clear?
Yes, sir.
So that is also the reason, building on this line, we want the depletion region to be as maximum as possible in a solar cell. So we would like to build a solar cell such that the depletion region is as maximum as possible, or more specifically, where the light falls on the device, that part should be in the depletion region. Okay, so that's why this geometry of the solar cell is a bit different. As you can see here, if we have high doping on N side, then almost all the P side will be depleted. So generally in junctions, what can happen is that if we dope one side very heavily, so if we dope, for example, N side very heavily, then P side is lightly doped, this depletion region will be more in the P side. And sometimes it may happen that this entire P side might be depleted. And that is the kind of diode that we generally have in solar cells, in which N side is heavily doped, so that this entire P side is almost a junction, is in the depletion region, and any electron hole pair that is generated in the P side or slightly into the N side as well, that is taken away from each other. The electrons and holes are taken away from each other. Okay, so there are many optimizations that we need to do. Uh, we need to block reflection of the light. We need to reduce the reflection. We need to design the solar cell in such a way that light is not reflected much. We want the maximum light to be absorbed in solar cells. So this solar cell design, and all of us know that solar is an extremely important electronic device, because this gives us very clean energy. This all of us know that uh, the it is the most popular way of harvesting the solar energy, and um, so this is still a very active area of research, making a better solar cell. How do we make more efficient solar cells? And that is even now a very active area of research. A lot of funding, a lot of research goes into this actually. Okay, so you may, maybe some of you might also think more about it. You can study about modern day solar cells as well. Modern day solar cells are, they work on the same basic principle essentially, but they have uh, nowadays very different geometries. Nowadays, very many thin layers of materials are used. Even quantum dots are used in solar cells. So you can also go through if you are interested in this, and if you want to discuss, we can also discuss this. Okay, so that is the essential mechanism of the solar cell as well. And uh, on the IV plot, this is the way it is shown. This is essentially, so in the first plot here is when we have a positive voltage, or we have the diode in the forward bias. In that case, this IV characteristics will be like this. So this is the IV characteristics when light is shining on the material. So the IV characteristics without light is this, but if the light is also there, the IV characteristics is modified in this way. Do you know the reason why it is modified in this way?
Sir, because the current is provided by the diode.
Current is, so in this case, as you can see that even at 0 voltage, if there is a battery connected, which means there is just a wire, there will be some current in the system because of the light. So even at 0 voltage here, there will be some current because of the solar light. Because the solar light that falls in the depletion region, that will create current. And that's why this plot starts from a negative value. And as we apply a positive voltage, first this current becomes 0 and then it becomes positive value. Okay, so this is the IV characteristics of a diode in presence of light. Please remember this. This is also very important, especially in optical devices, optical uh, diodes, solar cells especially, and photodiodes as well. In the first quadrant of this, the voltage is positive, the current is positive, and it means that the total power is positive and the power is being taken by the circuit. The power is dissipating. If you know the convention, if the net power is positive in a circuit, it means that it is consuming the power. Similarly, here in the third quadrant in reverse bias, voltage is negative, current is negative. So the product of voltage and current, P is equal to, is power, P is equal to P into I, is positive. So the diode is consuming the power. But in the fourth quadrant, the voltage is positive, the current is negative. The product of voltage and current is negative. It means that the diode is producing the power. So this is the quadrant in which the solar cell actually functions. And this is the quadrant where the power is generated by the diode or by the solar cell. Okay. So on the IV characteristics, we in solar cells, we operate in the fourth quadrant. Yes, there is a question, it seems.
In that fourth quadrant, the current is even less than the reverse saturation current. So how can we get the current?
The current is less than the reverse saturation. Sorry, I did not get it. No, the reverse
Like
saturation current. Yeah, so yeah, please don't confuse it. This is not the reverse saturation current. This current is reverse saturation current as well as the optically generated current. Because now the electron hole pairs. So please remember that this is the characteristics in presence of light. Okay, and in presence of light, a large number of electrons and holes are being generated, and that increases this reverse current quite a lot actually. So now this current is no longer microamperes or so, it may be milliamperes as well, depending on the intensity of the light. Do you get
yes,
it?
yes.
Yeah, it is
And so,
not the same IS that we had previously. Yes.
yes. So what is the difference between photodiode and solar cell?
Anybody among you knows about it?
Sir, in photodiode, only a small current is passed and it's in reverse bias. So that current is measured. It's actually used to measure current, while solar cell is used to generate electricity.
Okay, anyone else? So yes, so generally a photodiode, a PN junction is a PN junction, so to say, is a diode which converts light into electricity. Okay, it's a generic term. It may be used as a detector. So sometimes diodes are used as optical detectors. So where we need to detect photons of certain frequency or certain wavelength. Okay, but the solar cell is also, the working principle is the same, but the solar cell is purposed to convert the maximum light into maximum maximum as possible electrical signal, electricity. So the only difference between a general photodiode and a solar cell is that of the geometry or architecture. The principle is the same. Sometimes in photodiodes, we just need to detect a single photon or couple of photons. So we don't need to have this kind of geometry there. In solar cells, however, we need to capture as maximum solar energy as possible and convert it to as maximum electrical energy as possible. Okay, so the principle is the same, that geometry or architecture might be different. That's the only difference.
So in solar cell, first and second diagram are not important because we don't apply any external battery.
Yes, so it is just to show that these are not solar cells essentially. This is a forward bias diode. This is a reverse bias diode. And in forward bias diode, we have a power that is the diode consuming the power. In reverse bias also, the diode is consuming the power. But in this the fourth quadrant, when this diode is in the fourth quadrant, then the diode is producing power, and that's the regime of operation regime of the solar cell. Okay, so only this is the solar cell here.
Okay.
So please keep these working principles in mind. Actually, these are quite important applications, as you might have also realized that LEDs are extremely important for modern day technologies. Solar cells are extremely important as well, especially for uh, the energy needs of, or the increasing energy needs of humanity. And especially the solar cell is quite an active area of research even today. And as I told you, that there is a fundamental physical limitation to the efficiency of solar cells, and that is because of the stimulated emission, or that is also known as radiative recombination. Okay, so that essentially, yes.
Sir, like we studied that photodiode is always operated in reverse bias state. Sir, why is this so?
The reason for that is that in photodiode, we generally want to detect, or we generally want to convert optical signal to electrical signal. So in reverse bias, this depletion region is more, and if the depletion region is more, then only this photon generated electron hole pair will be converted into electrical signal. So that's why these photodiodes are generally operated in the reverse bias.
So, sir, like we have designed a circuit in which the photodiode is like operating in a reverse bias, and when light falls, the voltage on the negative n side will drop or it will increase. Like if I take a reference as 0 volt on n side, and when light is falling, will the voltage go to negative or it will increase to 1 or 2?
No, what are you maintaining the constant? Are you maintaining the voltage constant across the diode, or you maintaining the current constant across the diode?
The voltage constant.
So if there is a fixed battery applied,
Yes, sir.
so that is clear from this. Actually, that can be cleared from this diagram. So this is the typical IV characteristics. Okay, this is without light. So in reverse bias, let's say the diode is operating here. Okay, but as soon as the light falls, the diode, the current will increase. The negative current will increase if the voltage is kept constant, like this.
Okay.
Okay, so that can be understood from this plot. So this completes the applications of diodes, and let me not take much of your time. It is already I'm already including in your lunch time. But there are two important parameters that we need to keep in mind in solar cells. One is known as the open circuit voltage, and second is known as the short circuit current. So in as is clear from this plot, this diagram, IV characteristics, open circuit voltage is the voltage when the current in the system is 0, which means that this resistor is not there and we have opened up this circuit here. We have not connected anything here. In that case, the current will be 0, and this is the point where this will happen. Do you see this point on IV characteristics? This will be on the voltage axis, where current is 0, and in the fourth quadrant, this is the point. So this point, the voltage at this point is known as the open circuit voltage of the solar cell. Got it or not? Yeah, and similarly, the short circuit current is the current when this, instead of resistor, we have a short circuit, we just have a wire here, so that the voltage across the diode is 0 and maximum current flows through the diode, and that is the point here. So this is known as the short circuit current. So on IV characteristics curve, in the fourth quadrant, these two extreme points are, one corresponds to the open circuit voltage and second corresponds to the short circuit current. And these are important parameters in design of solar cells, although we will not discuss them in more details here. But just to keep in your mind, we generally prefer the more open circuit voltage and more short circuit current. Okay, so yeah, that's all about the applications of diodes. In the next class, we will see some circuits or the circuit approximation of diode, and we'll also quickly, now since we have discussed this diode in good detail, as you might have seen, the diode we have discussed in great detail. So we will quickly go through the BJTs, because BJT is a general extension or a very, I would say, natural extension of the theory of PN junctions. Okay. So next class, we'll see the diode circuits and BJTs. After that, we will, we'll also quickly discuss the MOSFETs, and then in 1 or 2 classes, we will see various circuits, various semiconducting circuits. Okay, and that will essentially complete this part. So, but in the mid-sem, since next class is I guess on Friday. Okay, let me see. I'll talk to your CR and then we'll decide about how to take classes. Okay. So that's all for the day, and thank you for joining the class on such a short notice.
Thank you, sir.
Yeah. See you soon. Bye bye.
Thank you,
sir.
Thank you, sir.
Thank you, sir.